The presentation title is CFRP Reinforced Concrete Columns Under Eccentric Loading. So the first one was the glass fiber, which is obviously different than the carbon fiber. The authors are Muhammad Charbadar and Professor Murat Saatcioglu. I can quickly say Professor Saatcioglu is a distinguished university professor and a university research chair in the Department of Civil Engineering at the University of Ottawa. You know, he's well involved in the CSA, Canadian Standard Association, SO8 standard on design, construction, building structure using FRP, and other standards, as well as ACI committees. So I can probably spend 5 minutes describing Professor Saatcioglu's bio. So, but with that, I'll leave the floor for him to present his work.
Thank you, Ali. It's very kind of you, the way you presented me. This afternoon, I will be summarizing experimental research that involved use of CFRP reinforcement in concrete columns as the main reinforcement as well as transverse reinforcement. I will basically summarize, first of all, the phase 1 of research, which was conducted under reverse cyclic loading. And then I will go to the main topic, which is the performance of columns under monotonically increasing eccentric loading. The first phase involved seismic research, and it included 12 square columns having 355 millimeters square cross sections. We used Ductile CFRP bars, either 8-bar arrangement or 12-bar arrangement, with different transverse reinforcement arrangements. Some of the bars were placed in the corners of NEFMAC grids that we used as transverse reinforcement, and others were only limited to the corners of the column, and I will show you pictures of that. The longitudinal reinforcement consisted of 9.5 millimeter diameter sand-coated CFRP Ductile bar. Sand coating was meant to help the bond, and NEFMAC grids had different number of cells, as you will see, and we tested either 2-meter long flexure dominant columns or 1-meter long shear dominant columns. They were subjected to different levels of constant axial compression and accompanied by transverse load reversals. So here you can see the construction stages of specimens with different shear spans and also cross-sectional dimensions. As you can see, we either had 8-bar arrangements or 12-bar arrangements using CFRP Ductile bars, and then subjected them to constant axial compression and lateral load reversals. In terms of failure and in terms of material behavior, we obviously did a lot of coupon tests, and our coupon tests agreed with what was specified by the manufacturer, and we went up to approximately 1,500 megapascals of tensile strength. In the second phase, when we tested columns under monotonically increasing load, we used Japanese bars, LeadLine bars, in which case we went up to 2,500 MPa. Here on this diagram, you see stress-strain relationships in tension and in compression. In tension, we went all the way up to the rupturing strain, and in compression, we were able to buckle the reinforcement. Tensile tests were conducted as we typically do with ends embedded in steel tubes with sufficient bond length to be able to break the specimens. For the compression tests, we have taken smaller samples and basically crushed them in the machine, and we were able to see the kind of buckling that was observed in our column tests. As you can see on the right-hand side, a couple of the columns failed due to compression, buckling of reinforcement, but this was not the same as the type of buckling we observe in steel reinforcement. There was no bending in the bars, but it was basically buckling of the fibers. And after buckling, the failure looks as if it was cut at that location, at the critical location. When we did analysis for validation, we used 25% of tensile capacity and 25% of modules of rupture as compression values, and in the case of foot-trowel bars, and 15% in the case of LeadLine bars, and we did obtain fairly good correlation. If we look at test data, I have reproduced only two hysteretic behavior. We were able to get some deformability. We went up to 2% without any strength decay, and at 2% concrete started crushing. And then gradually we started observing strength decay, but it is noteworthy that the unloading branches were passing almost through the origin, which indicates obviously that they remained elastic. So this was the restoring capability of FRP that we observed. If we look at the next hysteretic response, which is under 12-bar arrangements, we had similar behavior, and our conclusion from these reverse cyclic loading was that we were able to introduce some level of ductility and reasonable deformability, going up to 2% drift, and by essentially gradually crushing confined concrete rather than reaching the limits of the material. On the compression side, we were able to attain about 0.8% strain before bars buckled, and on the tension side, we were able to go up to 1% strain. So what was interesting was the observation that bars were able to develop significant compression strain, which was compatible with crushing of concrete, even though in our current CSA S806 standard, we disallow compression capacity of reinforcement when we design columns with CFRP bars. Now let's look at column tests under eccentric loading. We tested a total of 5 columns, and the objective of these tests, they were approximately 1.7 meter in height, and they were tested under universal testing machine. The objective was to see behavior of these bars in compression under different levels of eccentricity, and also to see if we can use the strain compatibility analysis that we always use for sectional analysis for steel reinforced concrete columns, and see if the same analytical techniques that we use for steel reinforced concrete columns are applicable to those columns reinforced with CFRP bars. And also, more importantly, develop column interaction diagrams for FRP reinforced columns, where, of course, the concept of yielding of reinforcement does not exist. And I will show you the correlation between interaction diagrams and the test results as well. The concrete strength on the day of testing was 55 MPa, and percentage of reinforcement was 0.36 when we used 4-bar arrangements, and it was twice the amount when we used 8-bar arrangement with eccentricities either 60 or 75 millimeters. Here you see stress-strain relationships for concrete. These are cylinder tests. So it's almost approaching high-strength concrete, and which is obviously compatible with high-strength reinforcement in this case. And then LeadLine coupon tests can be seen having over 2000 MPa capacity. And the table shows what was supplied by the manufacturer, which was verified by our coupon tests. In terms of transverse reinforcement, we use NEFMAC grids. These grids have had square or rectangular cross-section, 6 millimeters by 8 millimeters. And then we either had 4-cell grids or 6-cell grids. And we then used either 8-bar arrangements or 12-bar longitudinal bar arrangements with the dimensions that you see on the slide. The stress-strain relationship of NEFMAC CFRP reinforcement went all the way up to 1200 MPa. However, one has to understand that the critical point in these grids were the corners. And in this research, we did not observe any transverse reinforcement failure. However, in another companion research where we tested grids with steel reinforcements, longitudinal steel reinforcement, the corners started failing at about 700 MPa. So this 1200 MPa should not mislead you. That's the material capacity, but not necessarily lateral load capacity when it comes to restraining longitudinal reinforcement against buckling or confining concrete columns. This is our test setup, and the ends of the columns were externally confined because this was not the test region. And typical failure is, as you can see on the right-hand side, and the failure initiated with crushing of concrete followed by buckling of compression reinforcement. In 2 of the columns, we did observe tension failure in the bars. Only after buckling occurred on the compression side, and tension failure was in the form of rupturing of fibers, whereas compression failure was, as I have shown you earlier, as buckling of fibers rather than buckling of rebars. These diagrams summarizes test results. Here you see on the left-hand side, moment mid-height deflection. And obviously, as you increase eccentricity, moments increase at a faster rate. And also, the solid line without the data points is for the 12-bar arrangement, where we had twice as many bars, and hence it was stiffer than the companion column having same eccentricity, same 75 millimeter eccentricity. So there was nothing new about the moment mid-height deflection relationships, except we did reproduce these analytically using the conventional mechanics procedures and using basically sectional analysis, strength compatibility analysis, and integrating curvatures and getting displacements. So there was a good correlation in results. What I would like to emphasize is the measured strains in longitudinal reinforcement that you see on the right-hand side. Strain gauges were placed on extreme tension and extreme compression reinforcement. As you can see on the left-hand side, we were able to go up to about 0.3% strain, and sometimes we exceeded that, and the bars started bending and buckling. at about 0.4%. So this is compatible with what we take in our design calculations in Canada as 0.35% strain, and in the US 0.3% strain, which then means even though we do disallow contribution of FRP reinforcement in design purposes, they do maintain their integrity well after concrete crushing. On the right-hand side, we observed tensile behavior, and once again, we did get significant strains in tension. Next, I'd like to show you the interaction diagrams. These interaction diagrams were plotted either using unconfined concrete, in which case we used Hognestad's model, and analytically generated axial load moment interaction diagram. And obviously, the concept of balance section and tension behavior is different than that we deal with in steel reinforced columns. Our failure envelope was defined by either crushing of concrete or rupturing of FRP. As I said, in our test, we did not observe rupturing of FRP, but these interaction diagrams were plotted for that condition. And these are nominal interaction diagrams. And obviously, we have to use a phi factor and reduce the capacity by 25% to get design capacity. So design capacities will be well inside of these curves. And the confined concrete model was used to generate confined interaction diagrams, in which case the crushing of concrete was taken from the moment curvature relationship as the maximum crushing point on the interaction diagram, rather than assuming a strain value. Whereas for unconfined concrete interaction diagrams, we basically used epsilon CC of 0.0035 as per the Canadian standard. As you can see, the experimental curves, experimental points are indicated by solid square point, and they are at or near confined interaction diagrams, because these columns were mostly confined columns because the spacing of transverse reinforcement was either h/2 or h/4. So with this, I'd like to give a number of conclusions. Conclusion number one would be FRP reinforcement can be used in columns, in tension and in compression. Unlike the initial doubts, bars remain intact until after concrete crushes, even though because of the low percentage of reinforcement, FRP reinforcement, if you were to calculate contribution of compression reinforcement, that would not be that significant. But in terms of seismic behavior, because they maintain their integrity in compression, they are able to sustain stresses under load reversals. So when you reverse load in phase one, we observed this. Bars that were subjected to compression, when they were called upon taking tension, they were able to sustain same level of tensile stresses that we observed under monotonically increasing load. Also in terms of stress-strain relationship of CFRP bars, one has to establish elastic modulus as well as strength values. The two different types of CFRP bars we tested, namely Ductile and LeadLine, we got 25% of tensile capacity as compressive capacity and 25% of elastic modulus in tension as elastic modulus in compression. And these percentage reductions were 15% in the case of LeadLine reinforcement. Ductile bars had sand-coated bars, whereas LeadLine bars had deformations, and they maintained their bond capacity until after the crushing of concrete, and hence one can use well-established strain compatibility analysis for moment-curvature relationship, and we got fairly good agreement when we compared the analytical moment-curvature relationship with those recorded experimentally, and we obtained experimental values both from LVDTs in the middle section, which gives average curvatures, as well as strain gauges. Strain gauge data was not very close, even though it was close, because as you know, strain gauges pick up localized effects. But other than that, the conclusion in terms of applicability of mechanics principles is that one can analyze FRP reinforced concrete columns just as accurately as we do with steel reinforced concrete columns. In terms of behavior intention is concerned, obviously the design criteria would be based on crushing of concrete prior to rupturing of FRP reinforcement. And we did get quite consistent results when we designed concrete as confined concrete in terms of ductility and deformability. So under reverse cyclic loading, we were able to obtain 2% drift, essentially due to gradual crushing of confined concrete without rupturing tension reinforcement. And also the low elastic modulus that we have in FRP reinforcement works to our benefit in case of seismic resistance, because they do result in softer elements which tend to increase period of the structure, which reduces seismic force demand. So looking at it from that perspective, they can be used in earthquake resistant construction, perhaps for moderately ductile structures, and definitely under gravity loads in tension and compression. Thank you for your attention. If there's time and if you have questions, I'd be happy to answer them.